said, I'm going to turn it over to John Ingham from Dayton Development Coalition. He's going to tell you a little bit about the conference coming up in August. If you can sign in there, that'd be great.
All right, thanks, Jim. And before I do that, I'm John Ingham from the Dayton Development Coalition. I've been with them since February of this year. Prior to that, I worked for URS. I ran the local office here for 7 years. And prior to that, retired Air Force, 26 years. Before I start though, Jim, I was just thinking of something while you were speaking about attendance at these collider events. Do you open this up to, say, second to last year, juniors, seniors in the STEM?
Anybody can come to these.
Can many come? Is anybody here a student or a recent graduate?
No. We haven't had, not yet. We haven't had.
And the reason I was thinking about yesterday, I met with a young gentleman who just graduated from UC mechanical engineering, but he really wants to get into the aerospace industry.
Yes.
So I'm going to tell you what, I'm going to link him into this and
Sure.
do that.
Okay.
So Jim mentioned UAS Midwest. Has anybody participated in any of the 4 prior conferences we've held? They were called Ohio UAS before. So this year is going to be similar to last year's. We had a lot of lessons learned from prior years. It's the 16th and 17th of August. I have some flyers here, cards I'll be handing out. We are still open for exhibit sponsors, exhibitors, or just attendees. I'd highly encourage you to go take a look at the website, which is on here. And also, I'll have a stack of these by the front here. And if you don't mind, I'll leave them with you that you can distribute. But I'll hand out one for each of you. Basically, the theme of our UAS conference this year is partnership and collaboration. We're really focusing on not just Ohio, but the Midwest region, trying to tie together the industry and anybody who has got anything to do with UASs, from academia to industry to users, which could be farmers, precision agriculture is one of the things. So as the UAS culture is maturing, we're realizing that there's a lot more potential dollars and potential jobs creation in the applications phase of the UASs versus the manufacturing phase. So what I'm very interested in hearing from you. I'm going to also leave some of my business cards here if you're interested in talking to me about what we could do to make the UAS Midwest Conference a greater success. If you go online, the agenda is 90% complete. We have Steve Pennington, we have the Air Force Chief Scientist as a keynote speaker. We have several panels, to include one from AFRL. Reed, you're involved in that agenda formulation, correct?
That's right.
So you can also ask him. Unfortunately, I have to leave here about 3:15 at a teleconference, so I won't be around afterwards to talk if you'd like to. But anybody have any questions about UAS Midwest? It's Dayton Conference Center, the 16th and 17th of August. And again, you can find out all the information about registration right online. All right. Thanks.
All right. Gary.
Okay. My name's Gary Smith. Retired from AFRL like 3 years ago. What do I want to say? I'm getting thrust back into this, okay? And what I was going to do, I'm going to do a little overview. Talk about some engine components, some small heavy fuel engines, and a little bit of a submarine. Okay, I think when I first started this, okay, they asked me to do one little civil project on an engine, okay? And I thought, gee, that sounds like fun for about 9 months, okay? Well, I think 9 months turned into about 12 years. So I started this with one project, okay? And then we got to a certain point and I said, well, what do we really need to do to advance this technology? And we had a meeting. I had a meeting with an Army guy who's now retired too. But we were talking about what do we need to do to advance this technology. So we decided that, you know, commercial off-the-shelf components would not work for these small engines. Okay. So we decided we needed micro fuel injection, micro fuel pumps, turbochargers, power generation, so we needed everything on a much smaller scale. And it would have to be lightweight. A lot of these, some of these engines were using almost commercial off-the-shelf generators, which can weigh 7 or 8 pounds. So what we decided, and then I said, okay, now, how are we gonna get money to do this? You know? And somebody suggested, well, if you go to OSD and you have an Army and a Navy counterpart, you can get OSD money. So I go, well, okay, I got an Army guy, I gotta find a Navy guy. So it just so happens, there was a gentleman named Mike Gahn, who used to work across the hall in AFRL. He went out to China Lake, and he was actually working on the Ultra Endurance UAV, which was the Navy's, which has now become the RQ-21 Blackjack. So I said, okay, I said, Mike, I just want to use your name, you know, we're going to try and get money, you know. Okay. And actually, the stars must have aligned or something, because everything just fell into place. I mean, you know, so we submitted the projects, we got all the funding in, and we got started on all these phase 1 civils, okay? And I think that round, I got 142 proposals. And of course, my idea was, oh, I'll let the Army run some and the Navy run some. AFRL goes, no, you got to do them all. So, but you know, I had like 2 or 3 weeks to get 142 proposals done. And I mean, I was in there 7 days a week, 12 hours a day. But we did get through them. We got everything funded. And I will say this, I give the Army and the Navy credit. We all three worked together very well. As, you know, there are a lot of projects where you see the Army, the Navy, and the Air Force competing. We all realized that for UAS Propulsion, there wasn't a lot of money to go around. So any resources we could pool, we could get a lot more work done. But I just want to say, we did all the heavy lifting, okay? And so what we started is, the Army Shadow has a 38 horsepower rotary, okay? And that engine originally started its life as a Narcan motorcycle engine, okay? Believe it or not. So just about almost every engine we're using in UAS today started its life as for some other purpose. Whether it was a weed eater, a lawnmower, a motorcycle, you name it. And so, while that was where we were, and what it did, it had an effect on the time between overhaul, because most of these engines were running at wide open throttle, or close to wide open throttle, okay? And the life of an engine, you know, if you ran your car at wide open throttle, I don't know how long it would last, but it wouldn't be that long. So we have made some progress in that area. And one of the other things is, most of them ran on avgas, okay? Which in theater can be as much as $400 a gallon. So JPA is pretty plentiful, even diesel's pretty plentiful. So we started on this endeavor to try and convert engines to run heavy fuel. Now you have there's some small turbines out there. They just love JPA, not a problem. Okay, but rotary, the 110 horsepower Rotex on the Predator, it runs on avgas. So, and that engine there's 2 test cells over on the base. They call it in the Small Engine Research Lab, and they've probably been doing experiments on that engine for probably about 10 years. So they probably know more about the Rotex than Rotex themselves, okay? So, there's an engine called the Migraine combustion chamber. These guys manufacture it up in Chicago. I got some more charts on that one. Now the Cosworth, okay? That's a Navy engine, okay? The Air Force and the Army helped the Navy with the development of that engine. It is probably one of the only engines that is actually designed as a UAV propulsion system, okay? With the exception of the turbojet, okay? That's a 2-stroke compression ignition diesel, okay? And while I could put up a whole bunch of pictures of it, this is the only one I could pull off the internet that's not proprietary. So But I will say this, it's the only engine, it's 12 horsepower. The Navy wants to use it on the RQ-21 Blackjack. They have spent probably $6 to $8 million in development of that engine. So it is running, it has flown. I think they're working on integrating it into the RQ-21, which is gonna be one of the Navy's new airframes. So, and we will probably be doing some more work on that one. The Air Force actually helping the Navy out. You know, like I said, all us guys that are UAS Propulsion, you know, Army, Navy, Air Force, we all get along real well. I mean, most of us just want to advance UAS propulsion. So, and that will be, I would say, that's one of, I hate to say it, I hate to pick favorites, that's one of my favorite engines, okay? So, and then, these are just some of the engines we're using today. What we needed to do is, critical technologies were, you know, fuel injections, pumps, turbochargers, ignition systems, micro power generation, and we've actually done some work on propellers, okay? Now the problem with propellers is they make noise, okay? So this probably sounds a little silly, but the enemy actually uses dogs to detect propeller noise. You know, I can't hear them, but it's kind of strange. We did find this out at one point in time, so we started working on quiet propellers. So, and if you really think about it, okay, we make propellers, special propellers for C-130s and other aircraft. A lot of the UAV propellers are more or less hobby propellers. They're not actually designed as a specific component for a UAV. So that's one of the things we are going to have to work on. There's several propeller companies now, but one of the things we are going to have to do is really work on quiet propellers. So, okay, I'm going to talk a little bit. This is one of the several programs we did. It's called the Charged Fuel Injector. And without going in real deep into the theory, you put an electrical charge on a fuel droplet, and it actually breaks it into smaller droplets, okay? And so if you really think about this, if you remember from basic physics and electromechanics, plus, you know, if you put minus charges on each, they're going to repel. So you're going to get a pretty much homogeneous charge, okay? And it actually helps if you're going to run a fuel charge around, make a 90-degree, it'll actually coalesce when it makes that turn, so the droplets kind of run into each other and start forming bigger droplets. So we want, the magic number is about 10 microns to make these engines run on heavy fuel. So you got to actually make the droplets real small. And so we were actually able to accomplish that, and it was done with these little elements. And you could actually take a fuel charge, and if you put little plates in there, you could actually make you could actually make it turn on itself, make a 180-degree turn. So it was kind of neat. This is one of the few things that really hasn't made it to the field yet. We actually did use this in a CFR engine, and it worked, but it never found its way on board yet. So it's one of the few things that we haven't really got on board yet. Okay. Now, micro fuel injection. So that was a continuous system. This is a pulse system. So just like in almost any vehicle, it pulses. As you come up on compression, you dump the fuel in. Okay. And one of the problems we had is trying to use a diesel injector, which probably weighed 3 pounds, 3-4 pounds. So we actually had to come up with another generation of micro fuel injectors. And in order to make them work, you obviously have to have a pump, okay? And then in order to do the pulsing, you need a controller. So, and this is probably 3rd generation. The 1st generation we made, 2nd generation. We're probably pretty close right now to having a system with injectors, a pump, and a controller that can be adapted to most small engines. Now, what we have found is, I think we're at around a 50 cc limit. Okay, we're gonna try and do a 28 cc, but 50 cc seems to be, at the moment, the limit. But we are gonna start doing some experiments and look at doing a 28 cc. Now, the advantage of this is, several of the engines are compression ignition, so we've actually changed gasoline engines to run compression ignition, so you can, when you inject the fuel, you close off the exhaust port. With any two-stroke, normally you're throwing a little bit of charge out the exhaust port as the fuel comes up and charges the cylinder. So two-strokes are generally pretty, while they work well, they're inefficient. You lose a lot of SFC there. You don't get usually around 1.2. So one of the ones we did was this first one is a 55 cc. It's an off-the-shelf 55 cc engine. Normally runs on glow fuel or whatever you get from the hobby shop. And the SFC is probably about 1. Develops about 3-4 horsepower. And so this is probably not the first one, but it's one of the smallest engines we've done with micro fuel injection. So we were, and most people, they'll do a throttle body system, in other words, some sort of fuel charging device outside the cylinder. You definitely normally will lose 1% of your horsepower. So if you have a 5 horsepower engine, you may get 4 or 3.5 out of it. So we were actually able to maintain horsepower, and we got the SFC down to about 0.6. So we went, improved efficiency, got better SFC, and it seems to run pretty well on that. So the solution to the problem is injector, pump, controller. You need all 3 of those in order to make this system work. This has pretty much been adapted to several different engines, and it seems to work pretty well on all of them. So, and what I'm trying to say is we're trying to get ourselves off gasoline. They want one fuel in the field, JP5 for the Navy, JP8 for the Air Force. If worse comes to worse, you can always run on some pump diesel, okay? Okay, so I just set up a little spray demonstration. If I can get it to start. Up, I just turned everything on.
I get reading.
I'm trying to figure out which I can advance.
I can do it.
So this is generation 1 injectors, and we were actually measuring the soldering diameter of the fuel, and we also did a sort of a magnified, slow video of how it worked. And I mean, it worked flawlessly. It really did for the first generation. So, and I think we were spraying at probably about 6,000 psi, about 6,000 psi. So what you want to do is, you either got to do it one of 2 ways. You got to have a lot of pressure and run it through a pintle, or you have a lot of pressure and you push it through little holes in the injector nozzle. So the later ones, we're using the injector nozzle concept with a high pressure pump. So, and I think we're up in 14,000 psi range. So. Yep. Okay, so this is pretty much a summary of the injector, and we're up in, if you're not a 1,200 bar guy, it's about 14,000 psi. So about 30,000 injections per minute, and we can run up to about 10,000 RPM, and injection events 2 per engine cycle. So what we're trying to do now with compression ignition diesels, I don't know if anybody in here's got a diesel, but when you inject fuel, you're mixing it with air, and then you're compressing it, getting things hot enough, and it fires, okay? Well, there's a certain thing in there called ignition delay. It's called ignition delay time. So So as you mix the air with the fuel, you know, it heats up and then it fires. Okay, so in order to, you get a very violent spike, more than with the gasoline engine. So a lot of diesel engines, you have dual mass flywheels that, you know, kind of take up for that extremely heavy torque cycle. So on these small engines, what we want to do is kind of, it's called rate shaping. So you do two or three injections per cycle. So it'll bring that torque spike down, because on these small engines, you're probably going to have a lot of vibration, and you're also it's really going to be hard on the propeller when that hits. So what we want to do is do rate shaping, bring that torque spike down, and we can do that with an injector like this. So I can probably show you a little something here. That's the pump, about 14,000 PSI, 300 to 8,500 RPM. It'll run off an eccentric on your shaft, okay? It weighs about a half a pound, so, and pretty much on this injection system, you can probably pretty much tailor it for your engine, okay? You know, one size doesn't fit all, that's the way you want to look at it. Now, this is 55cc running on JP8. Everybody's sleeping, this will wake you up. So it actually does work. That's the micro injector on 55 cc's running JP8, maintaining horsepower of about 0.6 SFC. So, and we actually learned a lot on this one. Initially, we were starting it with a spark plug, you know, doing, if you will, hitting it with a spark until the engine got up to thermal efficiency, then we could check. And eventually we put a glow plug in it. So, just like a diesel engine. Keep the air up, it would fire right up. Only needed the glow plug for maybe a few seconds, maybe less than a minute. And once it heated up, it fired right off. And it does a nice job on JP8. It really does. So it's been adapted to about 3 or 4 different engines, including I think one Army engine that was a post-piston engine for power generation. So the system works well. Okay, and there's still some development to do, but the technology's been proven, and hopefully we'll be flying this pretty soon. And actually, the Cosworth engine, I think right now it's got Magneti Marelli injectors, but it actually has run this injection system and made 12 horsepower. So, and I think we're going to work on the Cosworth. One of the things we are going to work on is rate shaping. Bringing that, right now the Magneti Marellis run 1 pulse. So what we're going to do is put this injection system back in it, look at rate shaping and smoothing that torque spike out. And the Navy is extremely interested in putting this on the RQ-21. So the Air Force, being the nice guys we are, we're going to help them out. So also was this motor-driven micro fuel pump. Okay, a lot of times, you know, the other pump's mechanical, this one's electrical, okay? And it was actually designed for those instances. It could be, if you are running compression ignition, you need a lift pump. Most diesel engines, you have a lift pump till it gets to the injector pump. It could be used for that, or it can be used as a straight pump for either gasoline or diesel engine, a small engine. So. And most of the pumps out there today, or you buy it's a hobby pump. This one actually has its own, I should have brought one with me. It has its own internal controller. It's a 1 to 5 volt signal, 4 to 20 milliamps, or pulse width modulated. So you send it an input, you tell it what to do, and it does it. So it'll run, and this one particular, anywhere up to 3 bar, which is about 80 PSI, 70, 80 PSI. But the nice thing about it is most injection systems use a pressure regulator. Okay, this pump actually does the pressure regulating for you. Okay, so the nice thing about it, you can ramp it up, ramp it down. Usually it's on a 45-degree angle, and it's not particularly a heavy current draw. It's about 1.5 amps, and it'll work anywhere from 18 to 32 volts, and weighs about 1.25 pounds. And I'm thinking we could probably beat a little weight out of that yet. It's run for, I think we've run it continuously for a couple thousand hours without a failure. So the next thing we're gonna do is actually do some durability testing. So we're actually gonna flight test it. So, and if anybody in here has ever done any flight testing, it's very expensive. It takes about a year to fill out the paperwork to get it done, and you gotta have a place to do it. So depending on the size of the vehicle, I think there's a place over in Indiana that you can do it. I don't know if there's a big place around here. I know there's one over in Maryland, but depends on the size of the vehicle. Okay, micro turbochargers. One of the things that we discovered is when you get to altitude, you know, a lot of these engines need to stuff more air in, okay? If you go to high altitude, I mean, you run out of air when you get to maybe 10,000 feet, something like that. We've actually flamed a few of them out. They just didn't have enough air and they quit. So we did develop this micro turbocharger, and it weighs about 2.6 pounds, and it's got a variable geometry turbine. And I don't, anybody's a turbo guy in here, you know, okay? When you're at low RPM, you're not dumping in enough air. So if you have a VGT, you can keep that thing spooled up. And it's actually, it should be scalable. I guess it is saleable too, but it's scalable from 10 to 40 horsepower. I think we've used this on 38 horsepower. We're thinking now that we actually have to go smaller. For something like the Cosworth, it's normally aspirated. We need something down to about 10 horsepower. So this is actually, what would I say, a little too much weight. It can't buy its way on the Cosworth. So we're actually looking at something a little smaller than this for the Cosworth. But the Cosworth, it's a great engine, but it does lose it when they get to altitude. So we are going to look at developing a very small turbocharger for it. And this was kind of a fun project, really. You can buy a lot of automotive turbochargers right now, but I don't think you're going to find anything that weighs, you know, under, I don't know, the one on my Power Stroke diesel. It takes everything I have to get it out. So this one's kind of nice. I can carry it around. Cetane sensor. One of the things we did learn with JPA, I don't know if there's any fuel guys out here, that diesel engines like a cetane rating of about 45 to 50 to ignite. The lower that number is, the longer the ignition delay time. So, I hope there's no Navy guys in here, but anyway, they were running the Cosworth, and all of a sudden one day it wouldn't start. So they tore the engine down trying to figure out what was wrong. And then somebody suggested we should check the fuel. Well, it had a real low cetane rated fuel, so it wouldn't. And I believe this was one of the last servers I wrote up, was a cetane sensor. That CFR engine, which at the bottom weighs 1,900 pounds, it is the standard today. It was developed in 1928, okay? They still build those today. That is a standard for testing octane and cetane in fuel. Okay, so I had this idea. We need a quick and dirty way to check jet fuels for cetane ratings for these small engines we're going to run on JPA. Okay, and I actually wrote this one up, and it's pretty neat. I mean, I can carry it around. it takes just a little bitty sample, and it'll give you a readout in a minute of what the cetane is in the fuel. Now, my idea was, hey, I wanted a cetane sensor. I wanted it embedded in the controller, so it was real time, okay? So whatever the cetane rating is for fuel, it adjusts your injection timing, okay? And you're always at peak performance. So we haven't taken the next step yet, but I think this is a step in the right direction, because I'm sure some Marines could probably carry one of those machines around, but us Air Force guys, we're not that strong, so. But anyway, it's really a step in the right direction for, because I'm afraid, you know, when you get out there and you get a low cetane rating fuel and your injection timing isn't quite set right, you know, you're not gonna be at peak performance, so. And I think on the Cosworth, they had to advance the timing like 3 degrees, and it was like maybe a 33 cetane or a 32 cetane. So, and then actually you put it back together and start right up, but you know, it was a lesson learned, something you learn as we go along. Okay, catalytic glow plug. So a lot of these diesel engines we were looking at, the glow plug takes a lot of power to run. Okay, so I came up with this idea of a catalytic glow plug. Okay, so what happens is you energize the glow plug on cold start, you get the engine started. And actually what we found out is that the glow plug actually enhances your combustion, and you have a great decrease in the amount of smoke that comes out the tailpipe, because when you first start up, you're not at thermal efficiency yet. And actually, it helps you as you're running along. So it can be used in both turbines and ICs, but there's several engines out there using these now, and it's been pretty successful. Okay, the next thing is microcontrollers. Okay, UAVs, a lot of them are fairly lightweight. You can buy lots of commercial off-the-shelf controllers, but I used to have a little bit of a joke. I used to work on Joint Strike Fighter. It has a fuel-cooled controller, and I always say there's more fuel in that controller than in my UAV. But controller, one of the problems we have is having a lightweight controller that will do everything we want it to do, but we can't have the weight penalty of a commercial off-the-shelf controller anymore, because we are advanced technology, all the injections, the pumps, everything will run. So this is one of the ones, this is in a phase 2 right now, and it's tailorable for whatever, it can be tailored to your UAS platform, for whatever your input-output is. So, and I think the phase 2 just started like 3 or 4 months ago. So it's still in its infancy. But a lot of times, some of these companies didn't want to let their, I need this, that, and the other out, what they were doing on their engine. They wanted to keep it, so along with a commercial controller, you were kind of confined to what they do. So this one's more tailorable, for what you need. And the other thing we want to do is we want to do this rate shaping, so you got to have a controller that'll do this. So most of the bigger ones, the big diesel controllers will do that, but I don't think we can afford to carry one of those around and wait till it happens. So propeller technology. So while this isn't really related to JPA, one of the things we did do was develop propeller technology for UAV, so you could design a propeller for a UAV. And we wanted to also increase the efficiency and decrease the noise. So, and this one really came out nice, and we really wanted to flight test it. But unfortunately, as we flight tested, the money just wasn't there to do it. But it turned out to be a very good piece of work, And it's still there, waiting for us to use, so when we actually do start doing actual propeller work again, we're gonna test it. Mutating engine, this is one of the research engines, okay? And it goes anywhere, we built them anywhere from 5 to about 150 horsepower. And it's anybody know what the term mutating is? And, you know, we always used to get everybody saying mutating, and no, it doesn't mutate, okay? It's actually a disc that just kind of spins on a ball, okay? So this one actually has 4 chambers inside. You have 4 processes at 270 degrees. You get a power stroke every 180, and the center of mass is around the center. So it has some pretty big advantages in power to weight, having 2 power strokes per revolution. It'll run on JPA. This one is a smaller one, about 7 horsepower. We've had them all the way from 7 horsepower. We're working on the sealing. To seal this engine, there's radial seals, there's a lot of seals in this engine. So I think we're closing in on, completed the 3rd generation seal design, going to the 4th generation. So, and each time you fix one seal in the system, it usually taxes another seal in the system. So we're working on improving the ball seal now. But the nice thing about this engine, good power to weight, small package, and it will run on just about any fuel. So, yeah, of course it'll run on JPA pretty easy. Okay, migraine combustion chamber. Okay, if you want to think about this, it's a block inside an engine that's on a Scotch yoke. Okay, it's a very unique design developed by a gentleman up in Fort Wayne. It actually has 2 power chambers, if you will, and they call this the side engine, suction, induction, dual expansion. So this is actually a dual expansion engine, and it's very lightweight, and this is about a 2-hour brief in itself on how it works. But just to let you know, it does the original firing event expansion. There's another chamber below that it expands into. And so it's, by the time it exhausts, it's almost an ambient pressure. So it's a really neat engine. I actually own one, and I bought it on eBay. This company had a run of about 200 of them. And the advantage of this one is the propeller makes more noise than the engine. So it's a very quiet engine. It's easy to start. And I think one of the projects we had with this one was a permanent magnet generator. And it's very quiet, and that's the big advantage of this one. Okay, if you want quiet, you have to figure out, you know, and that's running an open exhaust. That's without a muffler. I mean, a straight pipe, if you will. So, and that's actually my engine on the test stand down there. So that's an FE 120, and it's about 2 horsepower. So. Okay, gas turbines, small gas turbines. Okay. With the rotary and almost every engine out there we're running, the big thing is time between overhaul. Okay, so the rotary, $200 maybe, $250 most. I mean, I think the Rotex 914 is probably about 1,000. They get about 1,000 hours on them. They you know, retire, done. Scan Eagle, maybe 400. So the nice thing about small turbines is you can easily get 2,500 hours time between overhaul. So they like JPA. They don't coke up like one of the problems we're seeing with running engines on JP8 is the oil that we're using for lubrication cannot take the intense heat of these small engines. So we're seeing deposits on pistons, exhaust ports, rings, and eventually you get enough deposits on that ring, it'll close up and you lose compression. So Nice thing about turbines, and this one's, 7.5 pounds, you know. Now, we don't have any accessories on that, but it still has SFC of 0.63. And it will run on JP5, JP8, Jet A diesel. And so I'm thinking that if we want longevity, time between overhaul, and you're gonna run the heck out of something all the time, you're probably gonna want some sort of a turbine powered UAV. So it could be a turbo shaft or a thrust engine, but either way. This is the turbocharged rotary JP8. This is the one they use on the Army Shadow. The Army Shadow runs on avgas. We actually converted this one to run JP8. On every one that everybody else has done, they've lost horsepower. We actually went from 38 to 42 horsepower. So we added the turbocharger. It'll give it a little more oomph. Runs on JP8, the micro injection system, and so we made 42.1 horsepower at 8120 RPM. So it is. So we've taken it from avgas to JP8, made the horsepower. Now the next thing is to work on materials and durability for this engine. Okay, if you ran this at 42 horsepower, I'm not quite sure exactly how long it would last, but we have gotten to the point where we can easily run these on JP8. But if you're gonna run them way out, like full open throttle, you're probably not gonna get the life out of it you want. So I would say this, all these projects, and I haven't covered everything we've done, but we've all reached TRL 6 and 7. Some of them are deployed, some of them are flying, not everything yet, you know. And getting over that bridge from development to actually flying as a product, it's pretty tough to get over that bridge. The heavy fuel conversions are showing really great progress. I think there's going to be some new component server topics to take up for, okay, now that we got everything running, we're experiencing secondary problems, okay, like oil coking, different, longevity items. So the next ones are probably going to be, let's see if possible propeller damper for small compression ignition engines, wide propeller designs, and I had this idea for morphing propellers. Okay, and if you know anything about materials, certain materials you put an electrical impulse in, they bend. Okay, so I was thinking if we can make a propeller and somehow impart an electrical charge on it, without having a mechanical means to, I don't want to claim to be an expert in this area right now, just an idea,
The AFRL is doing that, right? That's a research project at AFRL.
I'm not aware of that one. It could be.
I've seen photos of it.
Okay. Might be up in
It's in materials.
materials land? Okay. But I'm just saying, we put an electrical impulse in there and it morphs the propeller to where we want it to be, so without having some mechanical means to change the propeller. So.
The photographs I saw were on a wing, but the application would be the same.
Turbo alternators, rotary engines. On rotary engines, there's a lot of energy coming off that exhaust port. I mean, more than any other engine. So why not put that to good use? We could use that exhaust energy, build what I would call a turbine, put an alternator on the other side, we'll call it a turbo alternator, and probably generate enough power to get rid of the 7 or 8 pound generator they have on there now. One of the things we've discovered recently is lubrication oils. Okay. The problem being is you mix, for 2 strokes, you mix oil and gas, works perfectly. Okay. You mix oil and JPA, we're not sure. because what we're seeing is a lot of deposits on pistons, exhaust ports, rings, and the little analysis that we've done appears to be that the oil is breaking down. Now, is it because of we're mixing it with JPA, or is it because the engines are just running too hot? I'm not sure. Okay, so there may have to be, if you will, another generation of oils specifically designed for UAV applications. And material science, okay, looking at coatings on cylinders, pistons, heads, anything, bearings, anything that wears out. Non-lubricated rotary engine seals, we're looking at that. So there's these new SBIRs will be aimed at, what do I want to say, fixing problems that, because we've gone to JP8, we've discovered some downstream problems that we need to fix. So I think. And that's Greg and that's me, okay? So I haven't changed much, but this is actually the 150 horse mutating big engine there. So it's got a compressor and an expander. That's one of the smaller ones. Anyway, I think this was at AFA probably 7 or 8 years ago. So I've actually had cataract surgery since then, and I don't wear glasses. So actually, I'm getting better with age, I think. But anyway, Greg is now the Class 1 through Class 5 UAV propulsion lead over in AFRL. So I help him out from time to time. So yeah. Any questions? Yes.
You talked about fuel system modifications, ignition, glow plug modifications. You didn't talk about any. You're doing compression ignition, but you didn't talk about any modifications to the connecting rods or the crankshaft.
Well, I would say this, okay, if you're gonna run compression ignition, okay, and you take a commercial off-the-shelf engine like an OSG 255 or something, you're gonna have to do some bottom end work. They aren't, these are just experiments to see
Right.
what we can do, okay? And that's where I say the material science is gonna come in. We're gonna have to look at all these things, okay? If you're running compression ignition, you're gonna hammer that crankshaft and that connecting. Plus, the crankshaft, the propeller, all those things have to be looked at. So,
But you didn't have to.
Now,
to get compression ignition, you didn't have to modify the existing. We'll say it's 9.5 to 1 compression.
oh yeah.
You didn't have to take it to 22 or anything like that.
17, 16, 17.
Okay.
Actually, the OSG 255 has a different head on it. Actually, made our own head.
So you did it with the head. Okay.
Right. But like I said, now the Cosworth, that's actually designed for compression ignition.
Mhm.
So it was out of all these engines, the Cosworth, the Army, Air Force, and Navy have analyzed the heck out of that engine. There was a lot of analysis went into every piece of that. Okay, so if you take that engine, it was designed for that cycle. If you take, one of these other ones, we convert it, not, like the engine in the Scan Eagle, which is a 28cc, that's highly modified. It's 3W28 that's highly modified. So yes, all that is taken into account.
Okay.
So there's a bunch of Scan Eagles out there flying. It's pretty darn reliable, it really is. I'm not a big fan of catching stuff in nets when it lands, but so yes, you're exactly right. The OSG 255 was just an experiment to see if we could do it. It would not make its way onto the airframe without a heck of a lot of modifications. So. Yes.
Gary, how many of these applications you've described are moving along further?
I'd say just about
It's a
everything.
different
Just about
SBIR.
everything up there is.
They're all moving forward into
I'd say
the next phase?
with the exception of the charged fuel injection system, just about everything else is still going along, okay, it's still moving. So
And can you say who are some of the industry partners or developers or people working on these things?
Well, what it is like, Northwest UAV, a lot of the smaller, if you will, well, actually, I don't think there's not very many small UAV companies anymore, okay? Like, Northwest UAV is looking at using the fuel pump, they're all looking at using the fuel injection, okay? Cosworth, they'd like to have a micro turbocharger, so yeah, all this is really moving along. So the glow plug's being used in several applications, so. Propellers, we're probably gonna be moving along on propellers a little bit. Like I said, we're gonna keep everything moving, okay? And, we've had, what would I say, since I retired, and Greg's probably picked up in the last 6 months, things are starting to ramp back up, so let me say that. Yes?
With your multiple pulse injections in a cycle, are you running an injection post-ignition?
So you're talking about compression ignition?
Yeah, you said you were doing multiple pulse injections of
Right,
fuel.
right.
Is, say, the second pulse after ignition of the
No,
fuel that was first
absolutely
compressed?
not.
Okay.
It's during the combustion process, okay, so, and in fact, it is almost every commercial diesel, Ford, GM, they're all using, rate shaping, okay? Because at one time, they had these big dual mass flywheels, but it spread that injection out over several events. And I'm thinking we're probably gonna have to go to piezoelectric, okay? Because I think when we get 2 out of that, we might have to go to 4. So in order to do that, it's gonna have to be some sort of piezoelectric device that, instead of an electromechanical type actuator, they can go has a much faster pulse. Okay, so that's probably,
I think what he's getting at is it after it combusts? Like, is it all before, so you're squeezing air and fuel together?
oh, okay, I'm thinking.
Is it after it goes bang?
Yeah, has it
No,
started
it's
to
during
ignite?
it's during the combustion process.
Yeah, so you're
The
igniting
compression
during
cycle?
combustion.
Yes.
Okay.
Well, you're always going to go a little bit before top dead center, okay? Because you know, there is an ignition delay time. But yeah, you're gonna spread the pulse out.
Before the event?
Right. And it'd be 3 or 4, you know, we can do 2 now.
So you're not feeding a flame?
No.
Have you experimented with homogeneous injection?
Yes, some.
What
It's
results?
really tough to do. It really is tough to get a homogeneous charge.
What pressure is your turbocharger producing? What is the pressure, intake pressure of your turbocharger in the engine?
It couldn't quite get.
How much pressure is your turbocharger producing as it?
I think that one was a 2.2 pressure ratio.
Okay.
So, we're not, you know, for the turbo alternator and for the smaller one, you know, as you get smaller, your efficiency really suffers. So, and I'm not gonna try and make a prediction yet what we're gonna get to. It'll probably take some pretty genius design to get a turbocharger that big that'll work with the Cosworth, that'll be somewhat efficient.
Plus a lot of power.
Right. Yes.
Gary, where do you see the line drawn between using turboprop and not turboprop? I mean, where is that application space? Where's that line in the sand that says the prop isn't really the right way to go anymore? We need
If you wanna go
something,
fast,
we need something more than.
if you wanna go fast, then,
But given what you said about quiet,
right.
are you seeing any pullback or less interest in the future in the prop versus the no prop?
Not really.
No. Okay.
But, you know, there's been a couple of, let's say, BAAs out there They want it to go slow and they want it to go fast, you know, and well, you know, they want it to go, you know, beyond the propeller, so I'm sitting there going, well, sometimes you just can't have it both ways. You wanna go fast, you go fast, you wanna go slow, you go slow, okay, so a thrust engine probably isn't gonna get there, I'm not sure if the turboprop will either, so, you know what I'm saying? But whoever wrote that one up, you know, needed to think about
Wanted
it.
to have their cake and eat it too, right?
You know, you just change the wings and do this, that, and the other. Well, okay, I'm not an aerodynamicist, but I do know this, you know. You build an engine or a vehicle for a specific, if you will, most engines are built for a specific purpose, you know. It's gotta do this, so you design it for that. When you try and use it to do something else, like go slow, your SFC just, you know, takes a dump because you're not running at that efficient point. You know what I mean? So, but I think as far as turbines go, if you really want to get the time between the overhaul, you got to use the turbine. Because I mean, trying to think, the Army Shadow, that rotor goes about 250 hours, you know. And then they probably throw it away, put a brand new one. So, a lot of these engines, that's what they do. Now, if I'm an engine manufacturer, I love these guys, you know. Hey, well, it can depend on, you know, every 1,000 hours or so, I sell another engine, you know. So, and I said, that's what's nice about expendables. Hey, they can run up as many as they want, those 4 engines, right? But, no, you know, and so there's that mix, okay? You want a time between overhaul, you almost have to go turbine, you know? And I think the Scan Eagle, I was talking to those guys, they could probably get 1,000 hours up there, okay? Now, that's on gasoline, and when you start throwing JP8 in there, it's probably like 400 hours or 300 hours, okay, so.
Gary, you didn't mention hybrids at all, but do you see any potential for a nexus between this heavy fuels and a hybrid?
Yeah, they actually do.
I mean, we'll say if you took turbine, driving an alternator with hybrid technology, bring it together.
Yeah, I do
A
see
little
that.
bit of onboard storage for quiet.
Right.
So there's a potential nexus there.
I think you're gonna see more hybrids here in the future, so. I mean, it was, I'd say, the one I wrote up was just kind of an experiment to see, hey, do we gain anything or do we lose anything, right?
So there could be some more SBIRs, STRs in the pipeline for those.
Right.
Okay. Heavy fuel hybrid would be a great idea, wouldn't it?
Yeah, I think so. And it's like I said, it has to kind of prove itself, if you will. You know what I mean? So.
I just think that just like there are market drivers in the commercial world, there are logistics drivers, right, in the defense world. And getting avgas out of the logistics chain is a logistics driver, as strong as any market driver.
Well, and I always said, if there's any job I didn't want, it was being a tanker driver in country. So I don't mind hauling JP8, you can put bullets through the tanker all day and it'll just leak out on the ground. Gasoline, you know, avgas, no, that's not one of the jobs I want. Or, you know, hydrogen, you know, they were talking about hydrogen. Well, I don't want to be around, you know, filling something up with hydrogen if there's bullets flying around, you know, so.
Any other questions?
So anyway, I think you'll see this all spooling back up here shortly. Kind of stay tuned with AFRL. Watch what's going on. Like I said, I had all kinds of crazy ideas. Most of them will work.